from the University of Patmos. He speaks on integrable refactorization systems and Yang-Baxter maps.
Thank you. First of all, I would like to thank the organizers for inviting me here and giving me the chance to give this talk. So we will talk about some refactorization problems that are related with the Yang-Baxter maps and give rise to some integrable mappings. And this is a joint work with Professor Vasilis Papageorgiou from the Department of Mathematics of the University of Patras. Okay. So we will begin with a short introduction to refactorization systems and Yang-Baxter maps. So a refactorization system is consisting of a map S of this form here and two matrices L1 and L2 that depends from to a point of the set X and the spectral parameter such that this refactorization equation is in one holds. So we will call the order pair of matrices L1 and L2 Lax matrix, Lax pair. And also, if this equation here is uniquely solvable with respect to U and V, we will call the refactorization system strong refactorization system. And also the Lax pair is strong Lax pair. We can also put some parameters in our map. So parameter A goes with X and U, while parameter beta goes with Y and V. In this way, we derive parametric refactorization systems and parametric Lax pairs. And we can represent such a map at the edges of an elementary quadrilateral, like in this figure. We put initial values X and Y at these two edges, and we derive the final values U and V by applying this map. Now, what is a Yang-Baxter map? So this is also presented Yang-Baxter maps and also Mr. Fordy. And so it is just a map that satisfies this equation here, the Yang-Baxter equation. So it is better to see this on the cube. We put initial values X, Y, and Z at these edges of a cube. This is the same cube. This is the back side. This is the front side. And now we can derive the final values by two different ways. First, by applying the map at these edges here at the bottom face of the cube, we derive X prime and Y prime, and then at this face here to derive X prime and Z prime, and finally we derive these values here from the left face of the cube. Now, by beginning from the right face and then to go to the front face and then to the upper face, we can derive in a different way the final values. Now, if these final values are equal, then we will say that this map is a Yang-Baxter map. And the Lax matrix, a Lax matrix of a Yang-Baxter map, according to Veselov and Souris, is a matrix such that this system here, RLL, is a refactorization system. That means that this equation here holds for this map. Now, not all of the solutions of this equation here give rise to Yang-Baxter maps. A condition for this to be true is the next one. Then if RLL, that says that if RLL is a refactorization system on X, and also this equation here implies that the X, Y, and Z hat are equal to X, Y, and Z, then we can be sure that indeed this map R is a Yang-Baxter map. So here is an example. We begin with this Lax matrix L here, and now this refactorization equation implies that U1 and V2 will have these values but U2 and V1 will satisfy this equation here. So if we choose any solution of the last equation, we can derive a refactorization system of this form. But of course, not all of them are Yang-Baxter maps. An example of we can choose U2 to be equal to Y2 and V1 to be equal to X1, and then we derive this map here, which is indeed a Yang-Baxter map. And I think this map is related, in a sense, to the map that Maciek presented on Monday. So I will close this introduction by presenting the entwining Yang-Baxter equation. Now this equation involves three maps, SRT. So at each phase we apply a different map of the cube. At each phase of a cube we apply a different map according to this figure. And again we put initial values x, y, and z at these edges of the cube. And by applying these maps SRT and TRS, we derive with two different ways the final values here and here. And again, if the final values are equal, then we will say that these three maps satisfy the entwining Yang-Baxter equation. And this equation now is related in general with Lax triples instead of Lax pairs. But I will not go further to this entwining issue. Now we can consider, by beginning with a refactorization system, not necessarily a Yang-Baxter map, we can consider initial value problems on lattices. We have seen enough, many of them here. Also, Peter presented today some of them. This is the simplest, I think, one, the standard periodic staircase initial value problem, where we put initial values on a staircase on a lattice, x1 to xn and y1 to yn, and we also consider some periodic boundary condition. So from this point, all the values repeat. And we can define the transfer map as the map that takes these values to the values at the next step on the staircase. And also, we can define the K transfer map as the map that takes the initial values to the K step on the staircase. So it is the composition K times of the transfer map. I think we can also put some fixed boundary conditions, but this will be related to the reflection Yang-Baxter equation. And there is a nice poster of Contrelier outside with some details on this equation. But anyway, in this periodic boundary problem, we can define the monodromy matrix by the product of the Lax matrices of the Lax pairs from right to left. And now we can prove that the transfer map preserves the spectrum of the monodromy matrix. So from the spectrum of the monodromy matrix, we can derive first integrals of the transfer map. And of course, in order to claim integrability in the Arnold-Liouville sense, we need to equip the space of involution with Poisson structure. So in the case of polynomial Lax matrices, a very good choice is the Sklianin bracket that I present here. So we consider polynomial matrices n degree, m by m polynomial matrices. And the Sklianin bracket is given by this formula here, where R is the permutation matrix. Here on the left-hand side, we have the Poisson brackets of the coordinate functions. And here is the tensor product, the Kronecker product of the matrices L zeta and L eta. Now, this formula give us a nice Poisson structure on this space. Now, if we take which map? I don't have a map yet. I will come up to the map in a while, and yes, it will be. This is exactly the construction. So, first of all, if we take, first of all, the higher term matrix Xn, okay, the higher term matrix Xn here is a Casimir element. That means that belongs to the center of this Poisson algebra. Each element of this matrix is a Casimir function. And also, if we take the determinant of L zeta, I think here it is, and write it in this way, then all these functions f0, f1 to fm n are Casimir functions. And now we denote in this way the level sets of the Casimir functions, the section of the level sets. We put some constant values on the Casimir functions, and we denote by, in this way, CMN level 6, the section of the level 6 of the Casimir function. Here you can see, in the simple case of 2 by 2 first degree polynomial matrices, here is a Poisson structure matrix, and here we have F0, these two Casimirs, F0 and F1, of course, matrix A. And what we do in general is to consider some constant value, to put some constant values on the Casimir functions, and we solve this matrix, this equation here with respect to two elements of the matrix X. So in this way, we reduce the matrix L zeta to the level sets of the Casimir functions. And in this way, we construct Lax matrices. So we claim that this is a Lax matrix of a refactorization system. So here is an outline of the construction that we have presented. So it says that we begin with two invertible matrices A and B that commute with each other, and we construct L1 and L2 by reduction to the corresponding level sets, as I described before. Then we can prove that, that there is a unique map such that this equation, this refactorization equation, holds. So this means that this is a strong refactorization system. And now Yang-Baxter maps can arise in cases where L1 is equal to L2. Now, here is the answer to your question, yes. As you see here, by beginning for M is to be equal to 2, then we have first degree 2 by 2 polynomial matrices, linear polynomial matrices. Then this map that we derive in this way is a symplectic map with respect to the Sklianin bracket, the reduced Sklianin bracket on the symplectic leaf. We have also, in this case, classified the Lax matrices in 5 cases by Jordan normal forms. And also we have studied some initial value problems on the lattice, like the staircase case that I presented in order to examine if these maps, the transfer maps, are integrals. Now, we have these two nice properties of the Sklianin bracket. First of all, these maps here are Poisson, and in the symplectic leaves are reduced to symplectic maps. And also, the Sklianin bracket assures us that the integrals that we derive from the trace of the monodromy matrix will be in involution. Not only in this case, but in general, this is true due to a theorem of Babylon-Vialet. And so this construction, we can generalize this construction for M higher than 2. But in this case, the situation is more complicated because we have also lower dimensional symplectic leaves. But we can reduce our initial maps to these symplectic leaves to have, again, symplectic refactorization systems. And we can also apply all this to end-to-end Yang-Baxter maps in order to derive Lax triples and some examples of end-to-end Yang-Baxter maps. So here is an example of on the L21 case. So we consider here this matrix A. Here is a constant value epsilon. And now we have these two Casimir functions. We can set f0 to be equal to a and f1 to be equal to 1. We solve with respect to two elements of the matrix, and we derive this matrix. Now, according to the previous proposition, this equation here has a unique solution with respect to u1, u2, v1, v2. I haven't written the map, but there is an explicit formula for this map. It is just too long to write it. And it is a symplectic Yang-Baxter map with respect to the reduced Sklein bracket, which in this case is this one. Now, this is a non-degenerate map. Degenerate maps arise as limits of a non-degenerate in some cases. So here, if we send epsilon to 0, then we derive the Lax matrix that I presented before in the first example. And the Yang-Baxter map, the previous Yang-Baxter map, goes to this Yang-Baxter map, which is again symplectic with respect now the reduced Sklein bracket becomes the canonical Poisson bracket. Okay, I have an example on L3-1 with 3 by 3 polynomial Lax matrix, but I think I'll skip it. We reduce again, but now we can reduce to lower dimensional symplectic leaves in order to have a 4-dimensional Lax matrix. This one, and this map again is a Poisson map. Now, in order to proceed to construct higher degree polynomial Lax matrices, we consider n to the square refactorization systems, Sij, with Lax pairs Li and Lj respectively. And we can also consider this map here on Xn, on the Cartesian product Xn with Xn, that is defined by this composition of the maps here, but it is better to, I think, to understand this map here. So what we do is we have a big square that is consisting of n to the square small squares, and we put initial values x1 to xn at this edge here and y1 to yn at this edge here. At each elementary quadrilateral, we apply the map Sij. So by beginning with this square here, we derive these two values, and there's these two, and in this way we can derive all the values at each basic square. Now the map Sn, that with the formula that I presented before, is exactly the map that takes these values here and here to the values here and here to this big square. So in a sense is a composition of, in this sense, is a composition of the Sij maps. And now we can prove some facts about this map. First of all, Sn LL is a refactorization system, defines a refactorization system on Xn that with Lax matrix, the product of the Lax matrices L1 to Ln. That means that the refactorization equation holds also for this map here. Furthermore, if Sij satisfies the entwining Yang-Baxter equation, we can prove that this composed map Sn is a Yang-Baxter map with this Lax matrix here. And, this is just a corollary that we can begin with a Yang-Baxter map instead of a refactorization system Sij, and to compose this map with itself in order to have a Yang-Baxter map on xn times xn. So from a Yang-Baxter map on X, on this Cartesian product, we can derive always Yang-Baxter maps on this Cartesian product. And what about the integrability of this map? In a sense, it follows from the integrability of each refactorization system. First of all, we can, if Sij is a Poisson map, then also this map will be a Poisson map as a composition of Poisson maps. And now if we have considered the Sklein bracket on our phase space, then this matrix, this Lax matrix, which is the product of the Lax matrices, will also satisfy the Sklein formula. Now integrals of this map are derived from the trace of the corresponding monodromy matrix, which in this case is this product here of the two Lax matrices, and will be again in involution with respect to the Sklein bracket. Now, so what we do in general is to take a combination of products, a product of a combination of first-degree polynomial Lax matrices, and in this way we can derive n-degree polynomial Lax matrices. And one can, of course, ask if this case includes every case, that is, if every n-degree polynomial 2 by 2 Lax matrix can be decomposed in a product of linear Lax matrices. So, of course, this is a difficult question to be answered. So, for this reason, we would like to describe the symplectic leaves of the n-degree polynomial matrices. So, we consider these 5 special cases by reduction to the corresponding level 6 of the Casimir functions. Here you see the values that we put on the Casimir function, and here is the matrix A, the Casimir element A. And we can prove that for any constant matrix K and for any n product of L1 to L5 matrices, then this is a 2n-dimensional symplectic leaf of L2n. But again, one can ask the question if every 2n, if this describes all the 2n-dimensional symplectic leaves of L2n. So this is exactly the Sklein conjecture that say that any symplectic leaf of L2n can be decomposed into a product of a constant matrix K and linear matrix polynomials of this form L1 to L5. Of course, we don't know if this is true, but to this direction we have managed to prove a weaker proposition that says that for any choice of constant values alpha 0 to alpha 2 n minus 1, and for any matrix A, then there is at least one symplectic leaf of this form, where here P and K are invertible matrices, and M zeta is a product of linear polynomial matrices L1, L3, and 5, and product of these 3 matrices in any combination, such that the Casimir functions on this symplectic leaf to be exactly the initial values that we have chosen, alpha 0 to alpha 2 n minus 1. And so this is something. But again, we have to ask ourselves if every we find for each constant value of Casimir functions a symplectic leaf of this form, but is then every symplectic leaf can be described in this way? So again, we are not sure about this. This is something that we conjecture, and that we hope that someone will give a proof soon. Thank you very much.
Any questions, comments?
When you take the Scianian bracket with these 2 by 2 products, and is the bracket between, is it an ultra-local bracket at the level of the...
If it is a bracket, excuse me?
Is it ultra-local at the level of the factors? So I mean, if you...
What do you mean?
I mean that say you have L1 here, L2 here, L3, then the bracket between Li and Lj is 0 unless...
Yes, I think it was in once, but maybe I didn't say. Here is just, sorry. So, we have extended the Scianian bracket in this way to the Cartesian product, in the natural way. So it is 0 between L1 and L2. And in this way also in the big square, in each x we have the Scianian bracket, and in each y we have the Scianian bracket, and between x and y we have 0.
The reason I ask is because you had the staircase picture, and if you take
the staircase, yes.
Before. So if you take the staircase and you take the reductions of H1, for example, we have examples. You take the monodromy matrix, but the bracket that you get is not not ultra-local. So
in this case, you have to find some bracket between x and y. In our cases, we have some bracket between. Let's see this the staircase maybe. It is yes. It is no before this. Here we have 2 fields. So here, okay, it's just x1, but it is a vector with x1, x2, y1, y2, and things. So this is the bracket between these components here is 0, and we have bracket only in this. So for example, in the ABS list where we have only one field in each edge, then you have to figure a bracket between.
In all of it.
Yes.
Really. Yeah. Thank you.
Any other questions, comments, remarks?
Well, I was looking on the proof of the theorems that uniqueness, that what you call strong Lax pair, that means the only one or solution. But suppose our Lax pairs, polynomial in our variables, right? What means non-strong Lax pair? That means there are 2 or more solutions, right?
Yes.
So if you look from the point of algebraic geometry, that means we have, our variety is a union, and the ideal is not prime. So if you take a prime decomposition or take one leaf of this variety, maybe a restriction on the leaf or on a prime ideal will lead to Yang-Baxter map and the other restriction to each leaf. Some will give us trivial map like permutation, and some will give us this non-trivial. So I think this kind of requirement is excessive and can be just replaced by that what you restrict yourself on a irreducible variety, and on this let's explore that.
Maybe. So here it is an example of a not strong Lax matrix. So you see here, because we don't have unique solution, we have this here. So this gives rise to a correspondence. And okay, this is a Yang-Baxter map. I think also we can put a constant value here, a constant class here. But in general it is not. And also I think in general it is not Poisson. But this is Poisson. So with respect to the Scianian bracket, here the Scianian bracket is canonical. But of course, maybe this is true. What you said.
I have a question. No? If there is no further question, let's thank the speaker again.